Hello, welcome to the presentation of my algorithms course, homework 8. In this homework, I will solve problems related to breadth-first search algorithm on graphs. So now, let's start with a basic practice question on breadth-first search. Okay, so it gives me a problem. So let's read out the problem. So in a given undirected graph represented as an adjacency list, write a function to perform breadth-first search starting from a given source vertex and return the order in which the vertices are visited. So expected output should be like this. Okay, so now in this problem it asks me to write a basic breadth-first search algorithm. There is nothing fancy here. I think So I'm going to stop the video here. I will solve this problem. I will come back with the answer. Okay, so now I found the solution for this problem. So as you can see, I write a function called BFS as it just asks me in the question. Now let's see if it's correct or not. Okay, so ChatGPT says that my implementation of breadth-first search algorithm looks correct. Okay, so I think we are good with this problem. So now let me show you how I solve this problem. Okay, before moving on, I want to show you the graph that I use to track the progress of the breadth-first search algorithm. So I draw this because it's easier for me to understand. So let's see how a breadth-first search and a depth-first search algorithm works in this graph and compare them. So our starting vertex is A, as it's mentioned in the question. So in breadth-first search, we are starting from a starting vertex, which is A, and then we are going to check the neighbors of A, which is B and C. So our order will be, and right now, B, A, B, C. And then what would we do? We're going to continue with the neighbors of the neighbor B and C. So after that, we're going to continue with the neighbor of B, which is D, E. And then we are done with the neighbors of the neighbor B. We are not going to continue with H, because in breadth-first search, we are going to start from a starting vertex, and we're going to check its neighbors, and then we are going to only check the neighbors of that neighbor. And then when we become done with all of these vertices, we are going to check what's left in the graph. So we are not going to continue with H. So our order is going to be A, B, C, D, and E. And then we are going to continue with the neighbors of C, which is F and G, as you can see. So our order is going to be A, B, C, D, E, F, G, and then we are going to check. We are done with the neighbors of the starting vertex. So we are going to check what's left, which is only H. So our last vertex will be H in breadth-first search algorithm. So this is the case for the breadth-first search. Now let's see what will happen if we use a depth-first search algorithm on it. So in that first search algorithm, let's say we are starting from A again, and then we are going to check the first neighbor of A, which is B. And after visiting B, we are not going to visit C, just like we did in breadth-first search algorithm. Why? Because in that first search, we are not going to check the neighbors firstly. We're not going to check all the neighbors of the starting vertex in the first place. We are going to check the neighbors of the starting vertex. So we are going to continue with neighbors of B. So our order is A, B, and then we're going to continue with D and E. And then we're going to check if there is any neighbor that is connected to these nodes. Yes, we have an H. So our order is going to be A, B, D, E, and H. And then we are done with the components that is connected to the vertex B, and then we're going to continue with C. So this is the main difference between breadth first search algorithm and depth first search algorithm. And then after visiting C, it only has two vertices and there is nothing connected to them. So our order is going to be A, B, D, E, H, C, F, and G. So that's all about the graph representation of this problem. So now let's see the code implementation. Okay, so here's the code implementation of my algorithm. Okay, now let's start with the function. So the function's name is BFS as is just given in the problem. So it takes two parameters, a graph and a starting vertex. So at the beginning of the algorithm creates two empty lists called visited and line. So visited, as you can understand from its name, it stores the visited vertices in a graph, because in breadth first search and depth first search algorithm, all vertices can either be visited or not visited. So we are specifying the visited elements in order to not visiting them again. So we have another list called line. In this list we are adding elements. It's just like a queue. Just you can think of a queue. In the first line we have in the beginning of the line, the beginning of the queue, the first element is A, and then A done with its its process, A goes, and then the next element comes to the place, and then we are done. When we're done with it, we just let them go. As you can see, we are using a pop method to deleting the element from the list and printing out the list element to the user. So we have two lists, and after creating these two lists, we are adding our elements or starting vertex to these lists, visited and line. So we have a while loop here. So this works for only when line is not empty. So in the first line we have a variable called x, and this x stores a value, as I mentioned just right now. When we add an element to the index 0, now we have an only element, so it deletes it from the lists and stores that deleted element in x variable. So in the beginning we only have a, so x is going to be a in this case. So it's assigns the value at index 0 to the x. And then we have a for loop here. We are checking for the neighbors of the vertex x, and if neighbor is not visited, we are going to add it to or append. We are going to append that elements to the visited and line lists again. And then when we're done with the while loop, we're going to return the visited, which is stores the order of the elements. So now let's see how it works in practice. So in our graph we have this graph, as you can see. So we are starting from A, which is starting vertex is A, is given here. So we created the list and we added A to the visited and line lists. So the important list here is visited list. So the first element in visited is A. And then we are going to check why line is not empty. Why line is not empty right now, we just added an element. So we're going to pop A from the list, and we're going to check for the neighbors of A. So A has neighbors of B and C. So if neighbor is not visited, so we're going to check B firstly. B is not visited, we haven't added it to the list yet, so we're going to add B to both visited and line lists. So our order is right now is AB, and then we're going to check the next neighbor of A, which is C. C is also not in visited list, so we're going to add C to the visited and line lists also. So our order in visited list is A, B, C right now. And then now we are done with this for loop. Then we're going back to the beginning of the while loop. So in line lists we only have two elements, B and C, we have popped out A. So the elements in line list right now is B and C. So we're going to pop out the element at index 0, which is B. And we are going to check for the neighbors of B. So we have A, D, and E. So A is already in the visited list, so we are not going to add it. So D is not in visited, so we are going to add D to the visited list and also to the lined list. So our order is going to be A, B, C, D. And then we are going to check to the next neighbor of B, which is E, and then we are going to add it to our visited list and line lists. And we are done with the vertex B, and order is going to be A, B, C, D, and E. Okay, now what we will do, we will going to go back to the beginning of the list. So we have elements C, D, and E in the list line. So we are going to check for the C, so X is now C, and we're going to check for the neighbors of C, and the neighbors of C is A, F, and G. So A is already in the visited list, but F and G is not in visited list. So we are going to add F to the visited list and line list. So our order is going to be A, B, C, D, E, F, and then we're going to next neighbor, which is G. So G is also not in visited list, so we are going to add it to the lists. And our order is going to be A, B, C, D, E, F, and G. So now we are done with the vertex C, and then we're going to move to the D. So we are check for the neighbors of D, which is only B, and we already added to the element. We already added to the list. And then we're going to move to the next vertex, which is E, and we're going to pop it out from the list, and we're going to check for its neighbors. A has two neighbors, B and H. So B is already in the visited list, but H is not, so we're going to add H to the visited and line lists. So our order in the visited list is going to be A, B, C, D, E, F, G, H. And after that, we're going to start look for F, which is have only one neighbor, which is C, and it's already in visited list. And then we're going to move to G, and G has only one neighbor, which is C, and it's already in the list. And then our last element, H, and H is also added to the visited list. So that means that we are done with our graph. So while loop ends, because there is nothing left in the line list, and then it's going to return the visited. So let's see how it works. Does it work correctly? Yeah, as you can see. So what if we change the starting vertex? What happens? Let's see it. So let's say we're starting from the vertex B. So this is going to be our order. Or let's say we're starting from vertex G. Okay, so I think our function works correctly. So this is the solution of the problem. Okay, now I'm going to continue with another question, but it's a medium practice question. So now let's see what will it give us. So here's the problem. So in a given 2D grid representing a maze, the maze consists of open cells represented as 0 and walls represented as 1. And the entrance to the maze is located at 0, 0 and here. And the exit is located at the bottom right corner, which is here. So it asks me to write a function to determine if the maze is navigable from the entrance to the exit. You can move up, down, left, or right. And the expected output should be true. Okay, so I'm going to stop the video here, and I will implement this function, and we'll come back with the answer. Okay, now I found a solution for this problem, but I think there is a problem with this question, because it says that the expected output should be true, but it's not the case for this particular maze, because there is no road that connects this element to this element. Whenever you path you follow, you always end up with a wall here denoted as ones. So I think the expected output should be false at this point. So let's see what will ChatGPT say to us. Oh, okay, let's see a function, but when I just run the function in my computer, it says false here. Anyway, let's see how the function works. So this function is a little bit complicated than a basic breadth first search algorithm. So firstly, we need the imported DQ from the collections library of Python. It's going to be really useful for our function. So, and this is the name of the function. So, in the first line, we are defining the rows and columns, because in order to find a direction in the maze, we have to use the rows and columns number, finding a path. So the rows is equal to the length of the maze, and the columns is equal to length of the first element of the maze. And we have also an empty set called visited. We're putting the visited elements inside of this set. And we have directions. Directions 1, 0, minus 1, 0, 1, 0, and 0, minus 1. So these directions we are adding up to our current row or column values, and we move to the next element. For example, if we use this direction, let's say, or 1, 0, and let's say we are at the point of 2, 2. As you can see, let's say we are at this 2, the second column, and the second row, just 2 and 2. And if we add up this 1, 0 to it, what will happen? The row number will be 3, and it will come to here. So this means that we are moving downward. And when we use this is the opposite of this, so it's, we're going to move upward. And in here, let's say we have coordinates of 3 and 3, and if we add 1 to that, what will happen? We are going to move to right. And when we decrease it by 1, this means that we are moving to left. So this is the whole directions: up, down, left, and right. And we have an Q, which is by a DQ method. And we have a while loop here. So this while loop does the things by breadth first search algorithm. So while Q is not empty, so we have a row at the moment and column at the moment. This is the current row and column values, and we are retrieving the first element from that row and column values. And here we have an if block. This if block is really important because it defines whether we have reached to the destination, whether we have reached at this point, because this point is the end of the maze, as the function as the problem says. So if a row at the moment is equal to rows minus 1, which means that we are at the last row, and column at the moment equals to columns minus 1, which means that we are at the last column, so it corresponds to this point. If it is the case, then it will return true. So we have reached our destination. And otherwise, we're going to look for the direction and directions for the neighbor row, neighbor column. We are adding the directions, as I mentioned before. If our current coordinates are 2, 2, and we are adding the row, the 0 of this direction, which is 3, and we are adding the first element of that direction, which is 0, so it's going to be HW2 in that case. And after we are adding, we are going to check if the thing we have done is valid, right? Let's say we are at the roll number 0, and if I use a direction number like this, 0, -1, 0, what will happen? Our row number will be negative, so this can't be done, so it's going to be a false, so it won't continue on doing that. And it does the same thing for the columns. Let's say we are at the last column number, and when I add an extra column by this direction, I'm adding an extra column, I'm moving right, but there is no such column in that maze, so it's going to be a false. And neighbor row, a neighbor column is not visited, right? Because if it is visited, then this means that we are going backwards. We should not go backwards. We should always move forward. So it's going to give false in that case also. And here we are checking if the neighbor row and the neighbor column values are 0, because as the problem says, the only possible paths we can go are where the maze is 0, denoted as 0. And when there is a 1, this means that it's a wall. We cannot pass through there. So it should be 0 if we want to move through the maze. And after that, we are adding our neighbor row and neighbor column values to the queue and to the visited. Okay, so after that, we are going backwards to our next direction. We are adding directions for each element. We are checking if it is a valid approach. And after that, if this doesn't give us any true value, this means that we couldn't reach to the destination. So after while loop ends, it will return false, as it does in this case. As you can see, is a false because there is no such path that goes from this element to this element. So this is basically all about this problem. So I'm done with this homework.